Hello, I take it over from here. I want to show you that what the methodology that Robert has been talking about can be fully automated. As a matter of fact, Robert mentioned several times that the whole methodology is fully prescribed. However, in his presentation, there was a little bit of a hand waving, and several times he said that he would leave some details behind, hidden, because they would be tedious and the formulas would become so large that they would not fit on the screen. And first, when I was a PhD student, I started working on automation, and then one of my doctoral students, Diego Fabregat, took over, and he really went ahead and took care of all the minute details. And he also encoded a good amount of numerical linear algebra, of linear algebra rules, and put them into Mathematica. So now let me show you that this system, this is an interface that connects to Mathematica server back in Germany. And as I said, this Mathematica server knows this flame methodology that Robert presented, and it knows also quite a bit of linear algebra. Let's see what we can do. If I since you have heard about the Cl1ck factorization, let me go ahead and show how it can be automated. So there are two operands, one input and one output. L is an output, sorry about that, and it's a matrix, and it's lower triangular, and then we have a matrix A, which is an input matrix, and we know it's a symmetric, positive, definite. Okay, the operation that we want to perform is L times L transpose, and we want that to equal A. So this is everything that a system needs to know, and in fact this is everything that an expert would start with. Okay, I press OK. The equation, which is described by this precondition and postcondition, has been shipped to a Mathematica server. The first step was to automatically generate the partition matrix expression. Here it is. As you can see, there is only one for this specific operation. And from this partition matrix operation, 3 loop invariants were identified. The first one is then transformed into an algorithm, and as I loop over the loop invariants, the algorithms, the implementation changes. And I want to show you that if we click on details, all those details that Robert was talking about, so the loop invariant at the top of the loop, sorry, before the loop, and then at the top of the loop, and then at the bottom of the loop, all these predicates are shown, and it's then from the difference between these two predicates that the updates are described. Okay, so this is it for the Cholesky factorization. I want to show you that we can tackle significantly more involved equations. So I will talk about the Sylvester equation. Just to shorten, Sylvester. Okay, here we have 4 operands. We have a couple of triangular matrices, let's call them A and B. Then we have general matrix and the unknown matrix. So A is, let's say, lower triangular, B, let's also set it as lower triangular, C is just the general matrix, and X is the output matrix. And the Sylvester equation is defined like this: AX plus XB equals C. Once again, this is all the knowledge that is necessary to specify the equation, and it's all the knowledge that the symbolic system takes as input. Okay, the equation was a little bit more complicated, so it took a little bit longer. Here you go. This is the definition of the input. So the precondition and postcondition. Now the important thing to notice is that we don't have only one partition matrix expression, but we have three of them. So one, and for this one we identify two loop invariants. Second partition matrix expression, two more loop invariants, and then third partition matrix expression corresponding to a 2 by 2 partitioning of the matrix C and X. And for this we have 16 loop invariants. And as we march through these loop invariants, you see that the algorithm is automatically updated. Okay, just to show what was going on under the cover, you see that these are the algorithms, loop invariants, and the PMEs that came from a mathematical server. Let's see if I go up. I think that this is the, no. Yeah, this is still all the formulas. I wanted to show you the input, the expression that was sent to the, here you go, yes. So this is what we sent to the mathematical server, what we inputted, and then all those pages, all this garbage right here is the encoding of all these algorithms. And from the exact same encoding, we can either represent algorithms like this or generate C and MATLAB code. Okay, I'm gonna stop with this and pass it over to Robert again. Thank you.